Everything in the solar system moves in a disk. 8 planets, almost every moon, nearly every asteroid, all in roughly the same flat sheet. In 69 years of spaceflight, exactly one spacecraft has properly left it. And to get above the sun, that spacecraft first had to fly to Jupiter, 16 months in the wrong direction, 500 million kilometers out just to turn. That was not a mistake. That was the cheapest route anybody could find. Start with why the disk exists at all. 4.5 billion years ago, this was a cloud of gas and dust with a slight rotation. Not much, just a slight bias in one direction. As gravity pulled it inward, that rotation had nowhere to go. Angular momentum is conserved, it cannot be destroyed, only redistributed. So the cloud spun faster as it shrank, and material moving along the axis of rotation fell straight in, while material moving sideways was held out by its own motion. The cloud collapsed in one direction and stayed wide in the other. What is left is a plate, the sun in the middle, everything else circling in a thin sheet around it. Earth's orbit defines that sheet, we call it the ecliptic, and the sun's own equator is tilted from it by only about 7 degrees. How thin is thin? If you shrank the solar system out to Neptune down to the size of a dinner plate, the planets would all sit within the thickness of the china, not scattered through a sphere, pressed into a film. Every world you have ever heard of sits in this plate, which means every launch pad, every telescope, every human being who has ever lived has been inside it too. And that is not a coincidence of where we happen to be. It is the reason we exist at all. Planets form in disks, so anything living on a planet is, by definition, born inside one. Here is the part that makes escape hard, and it has nothing to do with rockets. Earth is not sitting still. It orbits the sun at about 30 kilometers per second. Not 30 kilometers per hour, per second. Roughly 107,000 kilometers an hour in a direction lying flat in the plane. Everything on Earth shares that motion. You do, your house does, and so does every rocket from the moment it is built. When a spacecraft launches, it does not start from zero. It starts already flying sideways at 30 kilometers per second in the plane, whether anyone wants that or not. To leave the plane, you do not add speed. You have to turn, and turning is far more expensive than going faster. Picture the spacecraft's velocity as an arrow 30 units long, lying flat. You want a new arrow of the same length, pointing straight up. To get there, you have to cancel the sideways arrow and build the vertical one. The engine has to supply the difference between the two. Work that out, and you get about 42 kilometers per second. That figure is the whole video. For comparison, the burn that sent Apollo from Earth orbit to the moon was around 3.2 kilometers per second. Getting a probe onto a path to Mars is roughly the same. Those numbers are already at the edge of what chemical rockets manage, and each one required a vehicle the size of a building. 42 kilometers per second is more than 13 times that, not 13 times harder. Rocket fuel does not scale in a straight line. Every extra bit of speed needs fuel, and that fuel needs more fuel to push it. The requirement grows exponentially. 13 times the velocity is not 13 times the rocket. It is a rocket that cannot be built. The European Space Agency puts it plainly. A direct launch into a polar orbit around the sun is not feasible. Not difficult. Not expensive. Not feasible. A different word. Chosen deliberately. Which brings us to Ulysses. Launched October 6th, 1990, from the Shuttle Discovery. A joint mission between ESA and NASA, and the only spacecraft that has ever flown properly over the sun's poles. It could not turn with engines. Nothing can. So it borrowed a planet instead. Ulysses flew outward, away from the sun, past Mars, all the way to Jupiter. It arrived on February 8, 1992, and swung close enough for Jupiter's gravity to bend its path southward, out of the plane entirely. The final orbit was inclined about 80 degrees. Almost perpendicular, it passed over the sun's south pole, then the north. That is the trick: to go up, go out, fly 16 months in the wrong direction, to the biggest gravity well available, and let it throw you. And even that was barely enough. The probe weighed 370 kilograms, less than a grand piano. Getting that much mass onto the Jupiter path took the space shuttle plus 3 additional upper stages. The bill for a piano-sized object to leave a flat sheet. Now the part that makes this genuinely difficult rather than merely expensive. Gravity assists are the only affordable way to change direction in deep space. Rockets add speed, Planets change course. Every long-range mission we have flown depends on them. But look at where the planets are. They are in the plane, all of them. They formed from the same collapsing disk, which is exactly why they orbit in it. So the only tool capable of getting you out of the plane is itself locked inside the plane. Every slingshot target sits in the sheet you are trying to escape. You can be flung upward, but only from below, by something that has never left either. That is the shape of the problem. It is not that we lack the engineering, it is that the solar system is built out of one flat thing, and the flat thing is also the only lever we have. The Voyagers show the same effect at smaller scale. Both left the plane. Voyager 1 tilted upward by roughly 35 degrees after Saturn, Voyager 2 pushed down by nearly 50 after Neptune. Neither was aiming to. The tilt was a side effect of the encounters that sent them outward. Granted by the last planets they happened to pass. Even leaving the disk, we leave it on the disk's terms. There is a second approach, and it is running right now. Solar Orbiter launched in 2020. Rather than one enormous kick from Jupiter, it uses Venus. Repeatedly. Each close pass tilts the orbit a little further. The result, after 7 years, is an inclination of about 24 degrees. With an extended mission, perhaps 33. 24 degrees. Ulysses managed 80 in a single flyby. That is the exchange. You either accept a decade of laps around the inner solar system for a modest tilt, or you spend 16 months flying to Jupiter and let it do everything at once. There is no third option. Nobody has found one. This is not a theoretical inconvenience. The sun's poles are where its magnetic field reverses. Every 11 years the polarity flips, and that flip drives the solar cycle. The sunspots, the flares, the storms that knock out satellites and power grids. We watch all of it from the side, from the plane, from the one viewpoint the sun's own geometry gives us. Ulysses flew over the poles 3 times, across 19 years, and was switched off in 2009. It remains the only spacecraft that has ever seen them properly. We have landed on Mars, flown past Pluto, and put a probe inside the sun's atmosphere. We have looked directly at the top of our own star exactly 3 times. The solar system is not a place with things scattered through it. It is a plate, and we live on the plate, and everything we have ever built started out moving with it at 30 kilometers a second. Going further out is a question of time. We can wait. Going up is a question of physics. 42 kilometers per second, from a standing start we do not have. One spacecraft has done it. It got there by flying the wrong way for 16 months and asking Jupiter for a favor. 36 years later, nobody has repeated it.